The second problem we're going to talk about solving recursively is kind of the classic Towers of Hanoi problem, which is something they use in a lot of textbooks as a way to introduce recursive algorithms and also as a kind of a, well, one is an example of something that's hard to solve without recursion, and two, as something that you can analyze in terms of big O, right, in terms of algorithm analysis, and you find out that it's something that's very slow, unusually slow. Its analysis will be unlike anything we've seen before, and that though we'll actually go into details on the next page. So Towers of Hanoi. What is Towers of Hanoi? So the idea is this: we have three sticks, right? That's what you see kind of in the middle, and then on one side, on the left side, we have a tower. And this tower is made up of some number of disks. So maybe it has n disks there. And each of these, right, has a certain size, right? So there's the largest one on the bottom, there's a slightly smaller one on top of that, and on top of that is a slightly smaller one, a slightly smaller one, and a slightly smaller one, right? So I have a tower of disks on one stick. And the puzzle is this: if I have a tower on one side, for example, my left, can I move them over to the right hand side, right? Well, more specifically than can I, how many steps does it take me to move them over, right? How many steps do I move over, does it take me to move them over? What steps are those going to be? In this puzzle, there's going to be three basic kind of rules, right, that say how we can move stuff around, right? Our goal is to move from one stick to another stick. So the rules are: first, you can never put a larger disk on top of a smaller disk. Second, you can only move one disk at a time. Third, every disk must be on a stick. As a very quick example, you could maybe imagine we could move this over here over to the second stick, right? So over here we have a disk, kind of. Over here, right, you can imagine you move this over here, slightly larger disk, right? So we'd have kind of stuff in different spaces, but then there's rules, right? So if I have this one over here, right, if I try to take off the third one, right, I can't put it over here, right? I can't do this, right? This is illegal, right? I can't try to put a bigger disk right on top of a smaller disk, right? And I also can't put it, over here because again, this is a smaller disk, right? I can't put something really large there. This doesn't work, right? So there's these basic rules, right? Move one disk at a time. Can't put a larger disk on top of a smaller disk. All disks must be on a stick. These rules, right, are summed up on this other slide. This is actually the one before it in the slide deck. So here at the bottom, you can see the three rules. And you're again, right, our goal is we want to move all the disks from one side to the other. And they're actually using here the term pegs instead of sticks, but close enough. So I guess I'll use the term pegs now. So this is our Towers of Hanoi, right? So let's see about how we could actually go about playing this game. Let's take a look at a very simple example. So here's our game. We have it set up with three pegs and a tower containing three disks. What I want to do, right, is I want to move all of them from one side to another side. So initially I have this configuration here, right, original configuration. So I'm going to have to follow my rules. I'm going to start by taking off one disk. And I could put it on either of these poles. It doesn't really matter. Let's go ahead and just put it over here. So first move, right, gets me there. Now I have this configuration. Tower over here, two disks, and then one part, right, the topmost small disk is over the other side. All right, so that's fine. That's a legal move, right? I didn't misplace anything. And then I can think about moving another one, right? So I can move this over here. So now I have them all spread out, right? Now it's this picture here. So I have one, and one. Okay, so they're spread out. Kind of haven't made that all that much progress, right? My goal was to move all of them to the right-hand side, and I haven't really done that yet. So what I'll do, right, is I want the biggest one, right, to be on the right-hand side. So what I'll do is I'll take this small one on the right-hand side, and I'll move it to the middle, right? So that gets me this picture here, right? I have the large on the left, and the two, kind of the medium one and the small one in the middle. Well, in that case, I can actually move my big disk all the way to the right. Now, this is great because I've actually managed to solve part of the puzzle, right? This disk here, right, that is actually now in its proper position, right? Its position in the solution, right, when I've moved all the disks to the right peg. So if you actually kind of look at this, what you'll maybe realize is that this part over here, that part is actually moving from peg. It's moving the first two discs from peg 1 to peg 2, right? So say this is 1, 2, 3. Well, our first part of our puzzle, right, is that we're taking those first discs, right, the discs, n minus 1 discs, if you would, and we're moving them to the middle peg, right? So in that case, right, I have a slightly smaller tower in the middle, and I'm free to move the big one from the left-hand side all the way to the right-hand side. So that looks pretty good. And let's continue. So I still need to move these other two. Well, what I'll do is I'll take this little one, move it back to the original one. So it goes over here. We end up over here, right? Fifth move, right? So we have these two spread out, and this one in its proper position. So at this point, we can move this one where it belongs, right? So this one is being moved, right? The medium one is being moved on top of the large one. And we get this down here, right? The small one is over here. The medium and the large are over here. Now, if we kind of jump back up for a second, which you may actually, well, it's hard to see here, but I'll tell you what's going on, is that we're again moving stuff around, right? We're moving. So at that point, we have those two there, and then we have make one more move. So we move our small one all the way to the end, right? So now we've reassembled our entire tower. So what this top part is doing is this is actually moving from peg 2 to peg 3. So there's actually three things happening here. First, we move kind of a smaller tower, right, n minus 1 tower to the middle, right, 1 to 2. Then we move the biggest disc, right, that's the one that I'm putting into its final position. And then I do another move where I go to the two, right, the n minus 1 discs, and I move those from 2 to 3, right? So I've moved them first to a temporary so I can move my big one. Then I move the temporary back on top of the big one. And then at the end, right, that's my kind of my general process. And here, right, I've moved all my discs from that first one to the left. And it took me a total of 7 moves to do that. So this is the puzzle. Let's think about how we would formalize this into an algorithm. On the next slide, they just give these kind of rules we talked to, right? So if we want to move n discs from the original peg to the destination peg, right? That's going to be a terminology, right? Original and destination. Well, what we're going to do is we're going to move n minus 1 disc, right, from the original to the extra peg, right? That was the first thing we did over here on the left-hand side. Then we move the largest disc, right, from the origin or the original, right, to the destination, right? So that's the diagonal here, right, where I'm moving this one to that one. And then once I've moved that one, I move the n minus 1 disc from the extra peg, right? So from the extra peg back to the destination, which is what we were doing over here on the right, right? So those 3 steps, right? As long as we do those 3 steps, that's kind of our general algorithm for solving this puzzle. The recursion here is coming into play because our whole size problem, right, our full size problem is to move n discs. And our sub problem, right, is to move n minus 1 discs twice. So that's our recursion, right? To move a tower, we need to move 2 slightly smaller towers and a disc. The base case in the recursive process is when we only have 1 disc to move, right? It's something that can be immediately moved. We don't have to take anything off the top of it in order to move it, right? It's already available for us to shift around. So one of the things we're going to see later is that the number of moves, right, in order to solve this puzzle, right, that's essentially what we're doing, right? We're going to simulate we're going to simulate these moves, and then we're going to calculate how many it takes. Well, when we do that, we'll see that it's going to end up looking like an exponential number of moves. And that's just something that we haven't really seen before, right? As an algorithm, it takes an exponential number of steps. Note that we're only going to be talking about this problem in terms of recursion. You could try to solve this iteratively if you wanted to, right, without using recursion, just using a bunch of loops, using a stack, basically, to manually manage stuff. But it's going to be very difficult. Recursion is going to give you the most natural way to solve this problem.